Good morning, our students, and welcome to this morning's class. Today, we'll be looking at a very important topic in statistics called continuous random variable. Continuous random variable. Continuous random variable. Permit me to write r dot v as random variable. And to better understand the concept of this continuous random variable, it is necessary that we look at other concepts and give it brief explanations to enhance our understanding of a continuous random variable. And what are these concepts? The concepts are one, we look at the concept of sample space, sample space. We look at the concept of a random variable on its own. Random variable. We equally look at the concept of what we call the range space. Range space. We look at the concepts called, or we look at what we call types of random variable. Types of random variable. Let us look at these concepts to enable us logically understand what is meant by continuous random variable. What is a sample space? A sample space is defined as the set that contains all the possible values of a random experiment or all the possible values of a random variable. That is what we define sample space to be. A set containing all the possible outcomes of a random experiment or all the possible values of a random variable. That is what we refer to as sample space. And this sample space is oftentimes denoted with a capital letter what S. And to explain clearer what is meant by this sample space, let us consider an experiment involving the rule of a Fay die. A Fay die contains 6 faces. So all the possible outcomes that we can have when a die is ruled, you can either have 1, or you have 2, or you have 3, or you have 4, down to 6. Beyond these numbers, you are not having an experiment involving the rule of a die. Therefore, 1 is an outcome of a rule of what? Of a die. 2 is an outcome of a rule of what? Of a die, down to 6. A set containing all these possible values or possible outcomes of this random experiment rule of a die is what we call a sample space. And therefore, in this context, it is going to be given as 1, 2, 3, 4, 5, 6. These are all the possible outcomes that is seen when a die is ruled. Let us equally consider the toss of a Fay coin. A Fay coin contains 2 unbiased faces described as a head and what? And a tail. Therefore, when a Fay coin is tossed up, it can either land with the head or it lands with the what? With the tail. These are the 2 possible outcomes of an experiment involving the toss of what? Of a coin. Therefore, the sample space is now going to be given as S, is given as what? Head, comma what? T, which is what? Tail. This is a sample space of an experiment involving the rule of a Fay die. This is a sample space of an experiment involving the toss of a Fay coin. What then becomes a random variable? A random variable is defined as a mathematical function that is defined on the sample space, which assigns numerical values or real values to all the outcomes of a random experiment. I repeat, it is a mathematical function or formula. It is always defined on a sample space. Its duty is to assign a real value or a numerical value to all the possible outcomes of a random experiment. That is what we call random variable. So what is now a range space? A range space is that set that contains all the real values assigned to all the possible values of a random experiment. A range space. It is a set. It contains the real values assigned to all the possible values of a random experiment. It is often denoted by R subscript X, where this X is a random variable. Or you talk about what R subscript Y. In this case, the random variable is a Y. That's what we call the range space. Therefore, if you come down here, we have what we call types of random variable. Random variables are classified categorically into two, based on the nature of the range sample space and the nature of the range space. And let us now begin to understand this classification based on the nature of the sample space and then the range space. When the sample space or the range space of a random what variable contains countably finite values, such random variable is described as discrete random variable. For instance, let us examine this sample space here that involved the role of what of a die. We ask ourselves, all the possible outcomes, are they countable? Are they finite? If you watch 1, 2, 3, 4, 5, 6, it contains countable values. It contains what? Countable values. Therefore, the experiment involving the role of what? A fair die is a discrete random variable or a discrete experiment. Let us come down to the sample space of the experiment involving the toss of a fair coin. All the possible outcomes, they are two in number, they are countable, 1, 2. Therefore, it equally involves discrete random variable. However, when the sample space or the range space of a random experiment contains uncountable values, we now describe such a random variable as continuous random variable. And the range space of a continuous random variable is often time denoted with interval of values. For instance, consider that the random variable x is a continuous random variable. And this continuous random variable s can take up all possible values between -2 less than or equal to small x less than or equal to what 3. This random variable x can take up any value small x between this -3 and 3 inclusive. And you bear with me that the values between -2 and 3 are of course uncountable, because it contains a lot of values between -2 and 3. And this random variable can take up all those possible values, which of course are uncountable. And that's the reason why we usually say that The probability that a random variable x, which is continuous, takes up a distinct value is always zero because it cannot take up a distinct value. It takes up all possible values between what? An interval. And you see them always right. The probability that this random variable x takes up a defined value a is always given as a zero. As long as this random variable x is a continuous random variable. That is now what we call a continuous random variable. So in a continuous random variable, the sample space and the range space, of course, they are uncountable. And they are made up of interval of what? Of values. Interval of what? Values. Something like from -2 to 3. Or from any defined what? Interval. That is what we call continuous random variable. So permit me to clean here while we talk about the probability density function of a continuous random variable. Permit me to clean. And before we talk about the probability density function of a continuous random variable, let us look at what we call types of continuous random variable or examples of continuous random variable. Examples of continuous random variable. Of continuous random variable, R dot V. Of course, weight is an example of a continuous random variable because your weight can take up any possible values between a certain range, can take up all possible values. Okay? So height is equally a continuous random variable. Then temperature is of course an example of a continuous random variable. Time is equally an example of a continuous random variable, and even distance is an example of a continuous random variable. These are unlike when you talk about the number of houses in a village, which is districts, because you can only go and count that number of houses 1, 2, down to the last one, without having occasions of fractions of values. But in these variables, there are possibilities of fractions of what values. So these are examples of continuous random variable. So we now talk about what we call the probability density function. Probability density function. Probability density function. Which is often written as PDF. PDF. And is always denoted as what? F of what? Of x. The probability density function, of course, it is a function that describes the probability of all the possible values of a continuous random variable, say x. I repeat, the probability density function PDF is a function that describes the probabilities of all the possible values of a continuous random variable x. This f of x, which of course is the PDF of a continuous random variable, has some properties. The properties is that this f of x is always greater than or equal to what? 0. That is to say that f of x is greater than or equal to what? 0. And then the number 2 property there is that 0 is less than or equal to f of x, which is less than or equal to what? 1. That is to say that the value of this PDF lies between 0 and 1 inclusive. It doesn't take negative values if value doesn't go beyond 1. And then The last but not the least is that the sum of this f of x over all the possible values of what of that x is going to give us 1. Because the sum of all the probabilities is what? Is 1. But when we are talking about continuous random variable, we don't talk about sum, we talk about integral. So we now say integral over the range of x of f of x is f of x dx is equals to 1. So these are the properties of the probability density function. It's always greater than or equal to 0. It lies between 0 and 1 inclusive. The integral of that f of x dx over this range of what? Of the variable x is always 1. We are going to take some questions on this probability density function to show us how to solve problems in probability density function. So permit me to click here. Let us look at this question I have here. Let us look at this question. So I will now target worked examples. Worked examples. Examples. Number one. Number one says, and I read, let x, capital X, let what x be a continuous random variable with PDF given as f of x is given as, here is 4x raised to power 3, here is 0. For the range 0 less than or equal to x less than or equal to 1, and then otherwise. And the question here says we should find P that x is less than or equal to 2 over 3. That we should find P of x greater than 1 over what? 3. And then that we should find P that x is less than or equal to 2 over 3, given that x is greater than 1 over 3. So we are to solve these problems given what the information they gave us. So I repeat, they say given that the random variable x has the PDF, probability density function, defined by this. Number one, we should find P of this. First of all, because they call it PDF, we have already known that it's a continuous random variable. And because they have given the range this way, of course, we know it's a continuous random variable. So the first thing they ask us is to find this. So for us to find this, what we are going to do is this solution. What this means is probability that x is less than or equal to what? 2 over 3. So when you are to find the probability of a continuous random variable, you integrate the function over the range that is given to you. And the range that is given to me here, x is less than or equal to what? 2 over 3. So I'm now going to say that P of capital X being less than or equal to 2 over 3 is going to be integral. The lower range of that random variable x is what? Is 0. So I'll start from 0. But I'm told that it is less than or equal to 2 over 3. So I'll stop at what? 2 over 3. What is the function given to me? So I say integral of this thing now, f of x dx. But I'm giving f of x to be this. What this means is that the function is f 4x raised to power 3 when this random variable x takes a value between 0 and 1 inclusive. But this value becomes 0 if this value of x does not lie between this range. That's what it means. So I will now say, so this thing implies integral from 0 to 2 over what 3. My f of x is this thing, 4x raised to power what 3, which is this. Here is my what? My dx. What am I going to do to integrate this now function now? For me to integrate this function now, I am going to add 1 to this 3, and the power becomes 4. And I will use that 4 to divide the what? The entire function. So this is now going to be, to integrate that now, I'm going to have now 4x raised to power 3 plus 1 all over. 3 plus 1 is what? 4 over the range from 0 to what? 2 over 3. From 0 to 2 over 3. Here there is 4, here there is 4, so I can easily cancel. So this and this is cancelled off. So I'm left with x raised to power 4 because 3 plus 1 is 4 over the range from 0 to what? To 2 over 3. To 2 over 3. So what is left here now is to evaluate this function when x is 2 over 3. Subtract it now when I evaluate it when it is what? 0. So this thing becomes, when this x becomes 2 over 3, what I have is 2 over 3 all raised to power what? 4 minus. When this x becomes 0, I have what? 0 all raised to power what? 4. And then 2 raised to power 4 means 2 times 2 times 2 times 2. It means 2 times 2 times 2 times 2. 2 times 2, 4, times 2, 8, times 2, 16. So this thing becomes 16 all over. 3 raised to power 4 means what? 3 times 3, 9, times 3, 27, times 3, 81. So this is 81. Which means the probability that x is less than or equal to 2 over 3 is 16 over 81. That is the probability. So permit me to quickly clean here while we solve this. So permit me to clean here. This one is probably that x is less than or equal to what? 2 over 3, which is integral from 0, which is the lower value here, stopping at that 2 over 3 here because it's less than or equal to it, of that f of x dx. And my f of x is given as this. Look at it here, dx. So I integrated this function here. I had 4 here and I had 4. They cancelled, so I'm left with this. Evaluated over this range, and we arrived at this. So permit me to click here. So the other one says I says P that my x is greater than 1 over what? 3. It is equally going to be integral. Now, this one says it is greater than 1 over 3. The other one says it was less than. When it was less than, we started with the least value here, which was 0. But this one is telling me that x is already greater than 1 over what? 3. So I'm going to start from that 1 over 3 and then end at the highest value of that range, which is what? 1. So I have f of x dx. This implies integral from 1 over 3 to 1. My f of x is given as this. So 4x raised to power 3. Then I have what? dx. As usual, integrating this, I'm going to have 4x raised to power 3 plus 1. Then all over. 3 plus 1 is what? 4 over the range 1 over 3 to 1. So that this and this is gone. And then this thing implies x raised to power what? 4 over the range 1 over what? 3 to 1. Here is 3 plus 1, which is this 4 here. So what am I going to do here? I will evaluate this function when x is 1, evaluate this function when x is 1 over 3. So in that case, what I now have here becomes what? When it is 1, I have 1 all raised to power 4 minus. So I will now come here, is 1 over what? 3 all raised to power what? 4. Which now becomes 1 minus. 1 raised to power 4 is 1 all over. 3 raised to power 4 is what? Is 81. And then I can say for convenience all over 1 and look for LCM of 1 and 81. And the LCM of 1 and 81 is what? Is 81. So 81 divided by 1 is 81. 81 times 1 is what? 81 minus. 81 divided by 81, 1. 1 times this is 1. 81 minus this will give me 80 all over 81. So the probability that the x is greater than what? 3 is 80 all over 81. See how these things are done. Okay? So permit me to quickly clean here. I'm not seeing anything difficult here, so we can solve many questions here. So permit me to clean this one. Remember, we got this one 80 over 83. Okay? All right. So we are the third one. The third one says the third one says we are now talking about a probability that x is less than or equal to what? 2 over 3, given that x is greater than 1 over what? 3. Anytime we want to solve this kind of a problem, we call it conditional probability. Probability that the x is less than or equal to 2 over 3, given the information that x is greater than what? 1 over 3. To solve this kind of a problem, what you do is this. That this is going to be probability that you now start from here, x is greater than 1 over 3. So you now say 1 over what? 3 less than what? X. Less than or equal to what? 2 over 3. 2 over what? 3. You close it. All over probability that x is greater than what? 1 over what? 3. I repeat. Any day you are giving this kind of, they gave us information here that x is greater than what? 1 over 3. Even if you come here, we still have that x is greater than 1 over 3. Here they told us that x is less than or equal to what? 2 over 3. Even if you come here, x is still less than or equal to what? 2 over 3. So any day they give you this kind of conditional probability and you have to evaluate it, use this idea. So x9 is at the center, but it's still greater than 1 over 3, which is what it is here, and it's still less than 2 over 3, which is what is here, divided by this probability, this information they gave us, that x is already greater than 1 over what? 3. So meaning, and we remember that what we have at the denominator here is what we solved earlier. We have already solved this one earlier. So we can easily now go solve the numerator and then divide with what we had here. Our numerator before was, our numerator here is the probability that 1 over what? 3 is less than what? X, and which is less than or equal to what? 2 over 3 is given as integral. You are now going to start from here and end from here. So you have 1 over what? 3 to 2 over what? 3 of our f of x is this. So we have f of x dx. This thing is now integral from 1 over what? 3 to what? 2 over what? 3 of 4x raised to power 2, 4x raised to power 3, sorry, dx. And of course, integrating this thing will give us what? 4x raised to power 3 plus 1 all over what? 4 over the range of what? 1 over what? 3 and then 2 over 3. And this thing implies x raised to power 4 over 1 over what? 3 and then 2 over 3. So you evaluate this thing when it is this and evaluate this thing when it is this. When we evaluated it earlier, we had that, I think that was 18 over, okay, let me evaluate it. So we now have something like this. When we put this value here, what we are going to have is 16 all over 8, 1. When we put this value here. But when we put this value here, we are going to have minus 1 all over 8, 1. You remember? if you put this value here, this 2 over 3 to be here, it becomes 2 raised to power 4, 16. 3 raised to power 4, 81. When you put this value here, it becomes 1 raised to power 4, 1. 3 raised to power 8, 81. LCM of this and this is 81. So you have that this thing becomes what? This is 81. 81 divided by 81, 1. 1 times 16. So 16 minus 1, you have 15. So that thing becomes 15 over 81. Because this 15 over 81, remember we are looking at this. And I have told us that we evaluated this one before to be 80 over 81. So this thing implies the numerator is 15 over 81. So I have 15 all over 81 divided by. What we had before was 80 over 81. So we have 80 all over 81. So what we are going to do now, it becomes 15 all over 81 multiplied by 81 all over 80. So that this can cancel this. And then we have the answer to be 15 all over 80. So the answer is 15 all over 80. Permit me to bring down my curtain. Let me see whether the clarity of this video can change. I think it is a little better. Okay, so that is how to go about this. We are going to drop the one that you help us try to evaluate. Let me clean here. This is number 2. Let us try and solve this number 2. Number 2 says, it says let x, this is number 2, let x be a continuous random variable with PDF defined as f of x equals x raised to power 3 all over 4 within the range of 0 less than x less than what? C. They now ask us, what is the value of C that can make this a true PDF? What is the value of C that can make this a true PDF? I will explain. For this to be a true PDF, it means that integral of this value over this range must give us 1. It is only when that thing happens that we call it a true PDF. That when we integrate this function over this range, the answer must be what? It must give us what? 1. So for us to solve this, I'm going to say integral, my marker, I'm going to say integral over the range of x, of f, of x, the x must give me 1. So I will now say therefore integral. The range they gave me is from 0 to c. So I have 0 to c. The function they gave me is x raised to power what? 3 all over what? 4 dx. So I will now integrate this. Integrating this means I should now add 1 here. So this thing implies x raised to power 3 plus 1 all over. I had a 4 here before, and I'm bringing 4 down again. 4 times 4 will give me 16. Over this range, from 0 to c. From 0 to what? To c. Remember, this must give me 1. Must give me 1. Now, this plus this will give me 4. So what I have is x raised to power 4 all over 16. From 0 to what? To c. Must give me 1. So I'm evaluating this thing when x equals to c. Evaluating this thing when x equals to c means it is going to be that c raised to power 4 all over what? 16 minus. I will evaluate it when it is 0, and then if you evaluate it when it is 0, everything is gone. So it is good as me saying this is equals to what? 1. I can say all over 1 to cross multiply. C raised to power 4 times 1 is what? C raised to power what? 4. This is equals to 16 times 1 is what? Is 16. Hey, this is not clear. So what is going to happen here is I can express this thing here now to be 4 raised to power 2. So that what I have is now c raised to power 4 is equals to 2 raised to power 4. 2 raised to power 4, because 2 raised to power 4 is 16. To enable me cancel this 4 and cancel this 4. And my c is equals to what? 2. So my c equals to 2 there. My c equals to 2. C equals to what? 2. My markers are becoming fainty, and then reflection coming from my windows are actually making the class to be a little bit the clarity is not giving me joy. So let me end the class now, and we continue solving problems on this in the subsequent class. Thank you very much for your audience. Don't forget to subscribe for us.